All right, looks like most everybody has joined. So welcome everybody, and thank you so much for attending this VRC webinar. We're really excited about it. If you're having trouble getting connected or hearing, please reach out to support@coldsprayactionteam.com, and we'll help you out for it. As I mentioned, we're here today for the VRC webinar where they're going to talk about all the great things they're doing in the cold spray world. Cold spray really, in my mind, has grown to what it is now because of people and organizations that have done so much to advance it. And also those people coming together and sharing, collaborating, and innovating together at events like this or at CSAT. And we at the Action Team really appreciate VRC's continued support for the event, which has truly been invaluable. Speaking of, and a quick reminder, and I'll remind you all again at the end, but if you haven't registered for CSAT or LSAT, please do so. We'll share the link down in the chat. It's coming up a bit over a month from now here in Worcester in May, and some of the events like the receptions afterwards are filling up. So I'd really encourage you to register for it, and we're very excited to have you there. With that, I want to introduce Tim Gellerson and Aaron Nardi, who are going to be speaking today. Tim has a tremendous amount of experience with over 30 years in the aerospace industry, expertise across many fields, and frankly, more connections than a flight from Burbank to Sri Lanka. And Aaron Nardi has been a key figure in the growth of cold spray at both the R&D and the commercial levels at UTRC, RTRC, the ARL, and now VRC as the CTO. He possesses a tremendous knowledge on the subject, but more importantly, is just a really great guy. And we all really appreciate everything he does and everything VRC does for the community. We'll do a quick Q&A at the end. Please use the Q&A chat at the bottom, and we'll dive into as many of those as we can. But with that, I'll kick it over to Tim and Aaron. Please take it away.
Perfect, Aaron. You want to go next slide first? Perfect. First of all, I want to thank everybody for joining today. Good morning, good afternoon, good evening. Like was brought up earlier, we are going to be tag teaming this today. It's going to be presenting to you. Normally, Aaron Nardi would actually present the whole gamut, but this year we thought this year would be a good time to maybe include somebody that's really good looking to jump in on this webinar. So here I am. So I'm going to kick it off with an introduction of what we're going to be doing in terms of outline. So we've got a VRC introduction, kind of a business model of what we have and the businesses across the area. We're going to talk about technology introduction, what we do from a technology perspective and the fundamentals. We're going to talk about our cold spray challenges that we have, that we've seen, and what we're doing to address those. And then how we actually are looking at maybe doing some additive manufacturing and the direction we're actually moving in terms of additive manufacturing. And then we'll follow up with questions. Next slide. So about VRC Metal Systems, we're a manufacturing technology company. Our main focus is on high pressure cold spray systems. We do wire DED as well, additive manufacturing. We also do friction stir welding, friction stir processes. We also do ESD, electric spark deposition, and other related manufacturing processes. The company was founded in 2013, and it was set out to commercialize R&D in the high pressure hand operated cold spray industry, working with ARL Army Research Laboratories, and then South Dakota State School of Mines and Technology. We're headquartered in Box Elder, South Dakota, with locations across the U.S., and I'll get into that in future slides. And one thing we want to put out there is we have over 100 systems sold to date, operating in 9 different countries. That's quite a bit of growth over the last 13 years. And then you see on the slide here too, some of the, if you look at the far left, some of the awards we've been given. We have awards for Small Business Export of the Year, Large Business of the Year, many innovations awards that have been given to us, America's Fastest Growing Private Company, and also some certifications from the likes of NSAIA, and also some, definitely some awards from some of the bigger OEMs like Lockheed Martin. One thing I'll point out is we also within our group have a FAA repair station that was brought on the company underneath the company umbrella probably about 2.5, 3 years ago. That company has now been awarded FAA Top 10 Repair Station of the Year last year. On the far right, you'll see some of the government partners we work with. We work with all 6 branches, as you can note here. The fourth one from your left is Department of Energy. So we do support all those, and we have great working partnerships with our commercial brethren. So we have Westinghouse, we have Raytheon, Blue Origin, Collins, Boeing, Caterpillar, to name a few. We also work with our research partners across the board. That is the likes of Penn State, Northeastern, WPI, University of Kentucky. We run the full gamut when it comes to research partners within the educational institutions. Next slide. So we talk about VRC capabilities and services. We offer cold spray engineering and manufacturing. So we design, we manufacture, complete our systems at our South Dakota headquarters facility. We also offer automation integration for cold spray and advanced manufacturing. One thing to note here is I would say, and I might be a little biased, but I really don't think so. We some have the best integrators in the world, in the industry. We also do advanced manufacturing R&D and applications development. That's on the lines of qualification support within industry, within companies. We also do sell spray consumables and prototypes, and that is in likes of powders, nozzles, etc. applications. So on the services side, the far right, we do repair, we do coatings, we do cold spray out of manufacturing, we do wire DED, we do friction stir welding, like I told you about before, friction stir processes and services, and we do electrospark deposition. So if you look at the slide on the far right there again, you'll see that the point of need services, we offer everything across the board. We offer not only stand up 100% turnkey, ready to go application within the company itself, but we also offer the portable needs and services out there to the market as well. Next slide. So our VRC family of companies, quite extensive and has grown larger over the last few years, as I had mentioned earlier. So headquarters is out of South Dakota. That does our systems engineering and manufacturing complete. And then we have our Novum Nano facility in South Dakota as well, which is our nanomaterial solutions. We have our Heartland Repair and Coatings, which is in Box Elder, South Dakota as well. And they specialize in pressurizing vessels, pressure vessels, manufacturing, and oil and gas services. And we added another company to the mix just recently, probably about 2.5 months ago, a company called CEF, and I'll get into that later slides. And then we go out to our supporting industries. We have Mid-America Aerotech out of West Fargo, North Dakota, which is process development, limited production, full production facility. We do work in Leominster as well as Webster. We do our cold spray research there with our wire DED and a process development, limited production there as well. And then we have our 2 maritime industries that are supporting at a VRC Chesapeake and VRC San Diego. Next slide. So I'll get into a little detail on each of those I just provided to you earlier. So the VRC repair production sites, this is we considered our maritime centers of excellence, and that is our Norfolk, Virginia facility, and then our San Diego, California facility. We are certified by the Navy for quality procedures for parts repair per the UIPI, which is the Uniform Industrial Process Instruction, I believe 6320-901. And we have portable capabilities to be able to perform field repair services as well. So what you see here is our standalone facility ready to support on-site with a full robotic setup. This is one of our facilities. I believe this is out of our Chesapeake facility. And in this facility, we're able to do the spraying, as you can see, full robotics, as you can see. We do the machining, as you can see, that is pre and post, fully CNC machines. And then we do have labs to do the lab testing as well, full support. So we do cold spray repair capacity mostly in these areas or these two facilities for the DoD. And we also do commercial sectors as well. And some of those commercial sectors we actually are concentrating or doing work with is BAE, MHI, Kelowna Shipyard, East Coast Valve, EMC. So the list goes on and on of the people we're supporting within the commercial sectors, mostly focused on the maritime industry. Next slide. This is Mid-America Aerotech, the facility out of Fargo, North Dakota. This is our Aerospace Center of Excellence. They do complete manufacturing, assembly, test and return to service of hydraulic and pneumatic components. These are complete LRUs, line replacement units. They go directly back on an aircraft, certified to fly, and can go out the door. We also do cold spray process development, qualification, and repair. We also do ESD there. We do electric spark deposition, development qualification. Matter of fact, we do have aircraft out there now that are using ESD as a way forward of fixing product that are flying across the Pacific Northwest right now. We have aerospace certifications. They're all the latest. We are AS 9100, AS 9110, ISO. We're FAA Part 145 repair station, and we are also EASA and UK certified as well. And you can see in these pictures, these are some of the products that we actually have fixed over the years. Like I said, a great background and a great communication across all of the major OEMs when it comes to aerospace, not only the OEMs, but also the tier 1, tier 2, and tier 3 suppliers. Next slide. This is Heartland Repair and Coatings in South Dakota. I mentioned them earlier. This is our Welding and Fab Center of Excellence. They are complete fabrication services, mostly concentrating on pressure vessels, some separators, catchers. They also do structural fabrication, mostly skids, spreader bars, and stands. And they also do piping fabrication as well. In the cold spray realm within the Heartland HRC, Heartland Repair Coatings, what they offer is for oil and gas heavy industry is a patented repair, pipe repair, including cold spray plus composite overwrap that we actually have the patent on now. They do other pipe and vessel coatings for corrosion and wear. And I had mentioned earlier in the slide about CEF, a new company that came on board, and I want to explain how it ties back to Heartland Repair Coatings. CEF stands for Self-Expanding Firefighting Foam. It's an advanced self-contained firefighting foam system. No water needed. It can put out a fire without the need for water. It's patented in North and South America. The commonality between CEF and Heartland Repair and Coatings is the pressure vessels. Those pressure vessels that are needed in this self-expanding firefighting foam is being actually fabricated by the likes of Heartland Repair and Coatings. So there's the combinations. And as you can see in the slides down below, we actually have a combination of what Heartland does in terms of the fabrication from tanks to separators, slug catchers. And then, of course, at the bottom here, the self-expanding firefighting foam and what it's done in terms of oil fire and being able to put it out without any water needed at all. And that's within 35 seconds. So next slide. Novum Nano. So this is our nanos material research lab. And that is up there in South Dakota as well. They identify nanomaterials that can improve performance across the board, right? Mostly on common engineering materials. They have functionalizing nanomaterials for improved homogenization. And one thing we got to keep in mind when we think about this is more of, think of it in terms of reduced particle means better distribution. That's what this means. And that's what they look for. So materials development and production, a lot of things they are actually concentrating on today are lubricating oils, the greases, the thermal grease, rain protection coatings, all those different things that we normally use in a normal industrial type settings. So prior work of this company is we have a Sibber phase 2. We have, looks like 3 of them that we actually that we're working now. one for conductive grease for avionics, rain corrosion coatings, composites, lubricity for engine oil, for fuel efficiency. And then the current work we're doing right now is another similar project, phase 2, development of a super oleophobic, sorry guys, floor coating for system for hangar floors that we're putting in play. Working with race teams to evaluate engine and gear oils, we're doing that as well, and lubricating greases. And we're also working with trucking companies to evaluate engine oils for fleet fuel efficiency. So we're into all those things currently. We're also collaborating with the Air Force to establish a CRADA for a flight evaluation on the rain erosion coating of the grease. So if you ever by chance see a bottle that you see up to the far right hand corner, or anything on the bottom left, far hand down the right, please pick up one of those bottles and support the cause, because it's a life changer and it'll be a game changer for you and your car. So next slide. VRC operation services. This is very, very important and near and dear to our heart. One thing that we always talk about is cold spray is a process that's easy to do. The problem with that is it's very difficult to do well. And we've seen that over and over again in the industry, where, you not only sell a system, but you want to sell the mindset of what is needed to make sure it's done properly. And there'll be a few times where we'll get a phone call back saying, it's not doing exactly what it said it was going to do, kind of thing. But that's where it comes in, the statement of it's hard to do well. It's the understanding what is needed to make it function properly based on that knowledge base that VRC brings to the table. So it is difficult. So what we do to help this out, we provide support options to accelerate and maintain a high return on investment. So we do enhanced cold spray operations training, and that could be an extended period of time that we're there for to support on site, to staggered training where we come in once a quarter to support the needs of the customer. We also do annual calibration services. We also do production maintenance applications, regular on-site visits to perform systems maintenance. We do reach back application support. So if there's something that is needed that they're experiencing, an issue they're experiencing, or they have a question about a way forward, they can reach back to our team of engineers for application support. Within that, we offer discounted prices on hardware and consumables. And then we also offer early access to prototype hardware and equipment that has not been released or put out there to the public as of yet. So this is full-time, also on-site operation support is an offering as we put out there as well. One thing I want to specify out there is that currently we have a full offering list of extended services with the capability to support all needs, all requirements. Cold spray is proven in the labs, right? It's proven, and it's proven in real world applications, but we need to push it in the commercial and push it to become commercialized. We need to make really cold spray a household name, and that's what we're doing at VRC. Thanks, Aaron.
All right. Well, thank you, Tim. Now you guys get to look at my ugly mug. All right, so I'm going to talk technology now, and I am going to focus on cold spray primarily, but I do want to introduce a couple of other technologies that VRC is investing a lot of time in developing also. So let's see. There we go. Cold spray, I think most of you are probably familiar with cold spray, but just for those, maybe new to the game, we're spraying powdered materials, and the deformation of those materials, the plastic deformation, the shock wave that occurs when the powder hits the substrate, that all plays into how those particles bond to the substrate and then to successive layers. So we do this with a lot of different materials. We, as VRC, primarily focus on high pressure cold spray, generally, in the pressure ranges that you see here. and temperature ranges as well. So that's kind of our focus. And when we do that, we look at a wide kind of variety of materials. And the nice thing about cold spray is you can spray these pure metals and alloys and things like that, which you've probably heard quite a bit about, with good quality, good mechanical properties and so forth. You can also, though, mix materials, and you'll see a lot more of that. We're seeing a lot more of that in the industry in general, but I mean, you'll see some more of that in my slides as well, because you can get some really unique benefits by being able to mix these materials in the solid state. Also, layered approaches where you want to do multiple layers, and even grading of those materials from one to the other. So there's a lot you can play around with on the sort of metallurgical side of things, and you can get some pretty unique properties. Tim mentioned friction stir. So this is a technology we actually procured production equipment as well as personnel to do this, and we're actually doing commercial operations in friction stir welding and processing of materials today. So this has been a kind of a new development over the past year. And we see a lot of synergy with this process and with the cold spray process. So there's a lot of benefits of combining technologies, and you'll see a little bit of that. But here you can kind of see the process takes a pin tool and it mixes the two materials together. Like if it's a weld joint, for instance, it'll mix those two materials together to fuse everything together, but it's doing it all plastically. So you're mixing the materials, you're not melting them, you're plastically deforming them together. And that's where that similarity to cold spray comes in. Now, what's really unique is you get this super fine grain structure that you can also process materials that are, you're not welding them together, you're just running the friction stir tool through it to enhance properties like ductility. So you see an example in the bottom right here of a projectile being shot through an aluminum plate before and after friction stir welding, and you can see that super plasticity of the material during that impact event. So what you can do with this now, and there's a lot of standard production processes now, and this is what we're actually doing commercially at this point, is welding of parts together. So here's a couple of examples, simple examples of cooling plates, right? Very big deal though, right? Especially in the aerospace industry and so forth, trying to cool your electronics and so forth. This makes a nice technique for producing very complicated geometries in your structural raw materials. So you can see there's a couple little examples here, one that's got a very complicated path of friction stir welding, and the other one that's a much simpler U shape. Now the friction stir welder, we have a couple of them now. One of the ones that you see in the image up at the top, that's what's actually being operated in the little video here. That system has a very large footprint, so you can do large parts, but and then it's got a certain sort of load capacity. The second machine we have is actually a 5-axis machine. So this is 3-axis. We have a 5-axis machine as well. So you could do much more complicated parts and much higher loads. So this machine can do, 1/4 inch, 1/2 inch of aluminum without too much difficulty. When you get much past that, you switch over to the higher load machine to do that work. Now, what's interesting is you can actually friction stir process a wide variety of materials too. So this video is actually friction stir processing a plate of aluminum. So this was cold sprayed aluminum. So we cold sprayed the aluminum. We've done a couple different examples to date where we've started with a higher spray process condition, and then we did another one with a low spray process condition. And even in the low spray process condition with a lot of porosity, you can consolidate that material and get really, really good mechanical properties. So that's kind of what you're seeing here. The other technology I'll just mention is the wire DED process. So in this process, you're taking what's a typical sort of fusion weld process. I'm showing two examples. These are the technologies we use at VRC. One is a gas metal arc welding, which is your MIG process, and the other is a plasma arc welding process. The main difference here is in the gas metal arc process, you're using the wire short circuit against the substrate to create your arc. And then as that wire feeds, you continually create that arc, and you're melting the material and so forth. There's certain characteristics of that process, but there's also certain limitations with what you can do with it. Like, for instance, you always have to have filler metal, right? You can't weld a material without filler metal, just melting the two materials together. Now, the plasma arc process is a little bit more like a TIG process, but instead of having the arc between your electrode and your substrate, you're actually creating this plasma jet with the arc, and that plasma jet, kind of like a laser, hits the substrate and heats up the substrate, and then you feed a wire, a filler metal, into that arc. So we use both processes. We actually use the plasma arc a little bit more often because you do have a lot more control over that process than you do with the more MIG-based process. Here's a few examples of what we're doing with it. So we're building parts, right? So making parts additively. That's really was our focus, when we started working with this process. And in some cases, you're doing that in an inert area. Like if you're doing titanium, you want to really control that atmosphere. And then other materials are a little less sensitive, steels and so forth. The shield gases are enough to protect those. We're also looking at other uses for the technology. You see examples down here where we've looked at cold sprayed copper, actually. And we've done a couple of different things to it. So the first one is copper in the as sprayed condition. The second one is if you take that as sprayed material and heat treat it, you're using a standard isothermal heat treat. And then the third image is actually an example of a plasma heated copper. So in this case, we're actually using the plasma, as many researchers use a laser to process the cold spray, either in situ or ex situ. And then the fourth image there is another variation on what you can do trying to tailor properties. So in this case, we're actually introducing another gas into the plasma process to actually try to create a composite structure in a titanium weld material. So you could see here pure titanium with titanium nitride formed within the structure of the titanium itself, hardening the material, providing wear resistance, and so forth. So with that, I'm going to jump back to cold spray and kind of talk about some of the challenges and some of the solutions that we've been working on for a variety of cold spray processes. So I guess one of the things to talk about is masking. Now, this seems like a fairly simple thing to do. You put a piece of sheet metal in front of your part and you stop the material from sticking where you don't want it, right? And that's really basically what we do. But there's a lot of little nuances to it. So, one thing is you see the little graphic there in the bottom left. When you put a piece of masking close to a substrate, but it's above the substrate like this, for instance, and then you stop once you get onto that mask, you can have deflection issues. What ends up happening is, and it's very material dependent, some materials are sensitive to this, others are not. But if you have deflections off of your mask, you can actually create defects in the first portion of that deposited material. So trying to manage where you have your mask, how you turn around on your mask, and so forth is really important. Now in the middle image there, you see just a standard raster pattern aluminum. And at either end of the aluminum deposit, you see this ski jump that occurs where the robot turns around. Anybody who's done cold spray has seen this. It's very common. Understanding that and understanding the defects that are going to occur in that turnaround area, as well as adjacent to this turnaround area, because of the same issue you had with your masking, you're going to get deflections off of that little ski jump, and those deflections are going to accumulate somewhere else in the material. Now that last image is there just to give you an idea of another potential challenge you could have when you're dealing with masking, which is if I take a piece of masking and I have it fixed, say in that left image, if I move that red piece of masking right down to the substrate and then I spray across it, depending on how I set that up, I could actually get welding of my mask to my coating that I want. And then that becomes a challenge for removal later. So the last image there on the right is an example of where we're purposely doing that. We have a steel piece of sheet metal and an aluminum piece of sheet metal, and we've created an overlap joint, and then we've welded the two together with cold spray. In this case, it was purposely done. We wanted a good bond joint, but you can kind of see that this process not only can be used for coating and additive like we're all doing, but it also it does secure materials together. Not exactly the same way as fusion welding, but it does do the job. All right, so similar to your masking issue, the way you blend a material makes a huge difference too. So you can see here an example on the bottom left. I've got two different methods of blending. The first one on the left of that image shows a very gentle radius, a large radius. I put there as a rough order of magnitude about 2 times the plume diameter. And we've found generally if you're in this very large curvature regime, you're going to have pretty good quality of your cold spray material. So you can follow that kind of a curvature with your plume if you want and get really good deposition quality. If you go much smaller than that, you will start to get particles that bounce and stick somewhere else, and that's where you start to get defects forming, porosity, and so forth. So I've got a couple images on the right-hand side here kind of showing that. Upper right, you see a aluminum spray. This was a helium sprayed aluminum material, so very high quality normally. But because we're spraying into this milled pocket, you're getting these defects that are forming right around the edge of that. And that's because you have a fairly small radius, and you're using kind of a flat raster pattern to spray there. So those secondary particle impacts, and especially when you're dealing with aluminum and spraying it with helium, there's a lot of energy in those particles. And if they do bounce off of a shallow angle impact, they still have enough energy to stick somewhere else. They just don't have enough energy to deform and bond well. So now you've got these defect sites. And the bottom right is a very similar issue. And then you've got robot path planning or nozzle path planning, right? So here you just see an example of a simple, fairly simple shape, a curved shape where you're applying a coating. And then down in the bottom left, you actually see a cylinder where we're spraying onto this cylinder just from one direction. So we're not spinning the cylinder or anything like that. And depending on the path you take across that cylinder, you can actually get very different results. So it may be tough to see, but the right-hand side of that deposit has a layered porosity structure where the left-hand side doesn't. And that's because of the sequencing of the raster pattern used on this part during the deposition. You also can clearly see the interface cracking, problems at the interface, again, because of how that material was laid down. And then the other thing I just threw on this slide is access. Like, how do you get your nozzle into a small area to try to access that small area? And then the last thing I'll leave you with as far as challenges go is more of the material selection and properties aspect. So generally speaking, a powder that's softer, a powder that is it's not significantly hard, sprays better. So you see here an example of 420 stainless steel that's been gas atomized. So in the gas atomized condition, this has untempered martensite. It's very brittle, very, very high hardness, and it doesn't really deform well and bond well. So you can also see a couple of other examples. One issue we run into is nozzle fouling. That's that middle image. And that's when we get a material that is really soft or has a lot of fines in it, or there's a lot of reasons for nozzle fouling, but that's another sort of pervasive issue that most everybody runs into at one time or another with cold spray. And then you've got your basic structural properties. How much ductility do you have in the material that you're depositing? All right. When we start talking about masking, here's just a couple of examples of the way it can be done successfully. So the upper left, you see a shaft. In this case, we're applying a material to that shaft, and we have a piece of hard masking adjacent to the land that we're depositing. Now, what's important to note, and it's tough to see there, is that masking, that piece of machined masking, is smaller in diameter than the diameter that we're coating on, so that those two don't bridge. So we don't want them to weld together. So we actually make it a little bit smaller. And now, similar to this image in the upper right here, any deflected particles are actually deflecting onto the masking rather than deflecting onto our deposit material. So that's kind of one way to think about addressing that. This other example in the bottom is a little tough to see because it's so well blended, but there's actually a steel piece in the middle, and then there's a washer around the outside of it. We then machined those two to have a perfectly seamless blend from the piece that we actually want the coating on to the washer. And what ends up happening is in the bottom right, you can see there's a copper-based alloy that's been applied to this steel. And as we work up to that seam, we bridge right across that seam. So in this case, we're actually trying to bridge across because we want to be able to machine that to a sharp corner afterwards. What you have to be careful about is now that has to be machined to remove that piece of masking because you've welded it to the part. As far as blending goes, very large, gentle blends are the best. You see the upper left image there. That's a large, gentle blend like you would use on most aerospace applications where you're trying to blend out pitting, porosity, things like that. And you can get very good fatigue performance when you do something like that with pretty much any material. So it could be your helium sprayed aluminum, like the examples I was showing before. There's no problem with pretty much any material when you spray into that gentle of a blend. Now, if you are spraying onto a more complex shape or into a more complex feature, that's where some of the alternative materials come in. So you see an image here, that same shaft that I was showing before being coated, from one direction in a raster pattern, but now you've got very good interface, you've got very good quality of your deposited material, and that's because of this unique blend that helps to create a very dense structure and well-bonded structure. And the same thing with this aluminum deposit you see on the bottom right. We've got a very sharp geometry that we're spraying into, and we still get very good quality. All those black dots are actually ceramic particles that are inside of that aluminum, and they're meant to be part of the deposit. As far as path planning, there's a few ways, a few things that are being done. The first is what you're probably familiar with, CSAM software, additive manufacturing software. There's several ways to create geometries and path plan that all virtually. Then go in onto your robot and make your part or whatever. There's also repair strategies, right? So there's obviously creating custom programs and so forth, but that takes a lot of time. There's also scan to plan type of technologies that are being developed. And we're actually working with a couple of universities as well as other suppliers, looking at a few of these technologies to be able to be used in shop environments or even in expeditionary use out in the field. Nozzle access, we've done a lot of work recently on new ID nozzle geometries to be able to get into diameters as small as 1.5 inches, and also be able to get very uniform depositions with those materials. Traditionally, when you start turning a corner with the cold spray material, you can end up with all of your powder on one side of your nozzle, for instance. You still can get a good deposit, but in certain cases that can cause you problems and it causes you irregular wear of your nozzle. These two new designs are based on a couple different concepts of eliminating that, and you can actually see from these patterns that have been created that we're actually getting a nice ring pattern of your powder. It's uniformly distributed within your nozzle now, so you get more uniform wear and erosion as well as a better build. There's a lot that's been done over the years with powder processing. You'll probably hear a lot more from Solvis on that in CSAT. We're doing a lot of work with a variety of different powders, looking at processing of those materials in different ways to get better quality. That's sizing, that's heat treating, that's a variety of other things that can be done to those powders. And then when you do it right and you start to look at additive manufacturing, you can get some really fantastic properties. This is just showing some fatigue properties of 420 stainless steel, but you'll actually see some more properties from materials in my CSAT presentation with Inconels and other aluminums and so forth. These are just a variety of different materials that have been developed over the years. Again, I mentioned before, these blends are very unique to cold spray because nothing that you put through the gun is going to melt. So it all ends up in your deposit in that solid state, in the same state that you put it in the powder feeder. The upper left here are some cobalt superalloys. These are very high temperature wear materials that have been created specifically for the aerospace industry. They're very, they have a need for very high temperature wear capability. See some bronzes, copper nickel based materials, iron based materials, 400 series, have a variety of austenitics and so forth as well. And then hard facing materials like tungsten carbide, and then some aluminum blends. And these are similar to what I showed a couple slides ago. And then, of course, you've got your pure metals and alloys with no secondary phases. And, there's too many to list them all. Here's just a quick snapshot of a few key materials that have been challenges in the industry in the past that we've had a lot of success with powder processing and sizing and making sure we get the input to the process just right. And one of the last things I'm going to leave you with is this thermal processing. I mean, I think we know that we can take a cold spray material and we can anneal it. We can do, a variety of different thermal processes to that deposit, and we can get some very nice mechanical properties out of it. I wanted to show this because it shows what even a very mild, for the material, what a fairly mild processing does. This is an austenitic-based stainless steel blend that uses a chrome carbide as a secondary phase. That secondary phase helps you eliminate nozzle fouling. It also helps to consolidate that material really, really well and give you some wear resistance. In the right-hand side of this image is actually after a very mild heat treatment. You see here it's only 500 C, which for austenitic stainless steel is still pretty low. It was a long time in the furnace though, at 24 hours. So this is what you might expect if you actually put this material into service at these types of temperatures as well. And you actually see a hardening response. You see it go from 430 Vickers up to 520. And that's a little bit of diffusion that's going on between that secondary hard phase, which is actually strengthening the deposit a little bit in that final condition. And this is where I'll end. Just a few last ideas. Sensors, a lot of work with sensors, whether it's powder feed rate sensing, velocity, nozzle performance. There's a lot of work being done in that area. And then secondary processing. So I mentioned all the thermal processing, whether it's in situ or ex situ. And also friction stir processing of these materials. And with that, if anybody's got questions for either myself or Tim, happy to answer them.
All right. Well, thank you very much, Aaron. We can hop right into these right now. Got one right here for repair via cold spray and similar technologies. What do you see as the needs to be met for their usage to expand, both in a technological and a regulatory sense?
So I guess technologically, I mean, I think there's been so much done in the repair space. I think it's almost we're at what can't be done sort of thing. There's I think your big hurdles are not technical. They're really in the regulatory space. And I would say I'll actually let Tim answer that because he's very familiar with the regulatory space, especially for aerospace. So I don't know, Tim, if you want to expand on that aspect of it.
Sure. So yeah, regulatory is I would say is one of our biggest hurdles, and maybe I wouldn't call it a hurdle. It's more of what's required to get across the goal line. Is it a challenge? Sure, it's a challenge, but I think VRC's actually cracked the code on what's required when it comes to getting it across the goal line for these industries to approve, these governing entities to approve, I should say. The FAA, of course, and then the ABS on the maritime side. We kind of have that figured out now, what they're looking for in terms of data, detail, verbiage that's needed to support getting it approved faster than it has before. So it is still a challenge, but I think, like I said, VRC has it figured out on how to proceed.
Okay. Thank you very much. Let's see. Another question here we have is one thing that a lot of engineers and technical types struggle with is taking the technology they are good at and using it in new applications. It's something you all are very good at. And can you talk a little about how you're so successful at it?
Yeah. So I guess being creative, right? It's trying to see what the best aspects of a technology are, what make it unique. And then kind of going after I know others call it like low-hanging fruit, but I say it's really where the pain points are, right? Like let's use cold spray as an example. So we have cold spray. What is it really good at? It's really good at depositing materials in the solid state without a lot of heat input to your substrate. It's not necessarily the same as fusion welding or friction stir welding or whatever, but it's easy to apply material onto wide variety of substrates. So that's why repair has been a natural fit for it, right? Mm-hmm. VRC specifically also saw the benefit in portability. Like, how do we take this capability and bring it into the field? That becomes really important because I look at it from like kind of two different directions. One is I can have a really expensive part and I want to save that part, right? That's the aerospace model. I got these really expensive aerospace parts. I want to save them. There's a lot of value in being able to cold spray those and fix them. But there's also those like immovable objects, right? You got those things that you just can't take out of the field for one reason or another. And so being able to take that capability and go to the product is really valuable. So, we try to expand on those types of areas and see, okay, how many of those types of applications are out there? Let's go explore that space and try to, again, meet the process where there's a lot of value. Now, on the opposite side, say I've got a very low cost, part that's like, $50, $100, something like that, trying to come up with a model where you're going to use cold spray to repair a very low cost item, that's a big challenge, right? And that's where we've kind of put the brakes on a little bit, is trying to go after those particular applications unless we can make a so if we can add value to that part by putting a coating on, so if we can take a part that was only good for 100 hours and now it's good for 1,000 hours and we can upsell that to the customer, well, that's a different story. But if you're just trying to repair a part that's really inexpensive and somebody can get it, next day, it's a tough sell. So hope that helps.
Yeah. I have another question here. On-site repair can be a difficult thing to do. What do you see as the next kind of direction for improving mobile and portable cold spray systems?
So I think we're in a pretty good spot with the cold spray system itself. What's a little bit of a challenge, what we find in, our trials, is all of the surrounding equipment, right? The cold spray system, we got that pretty well taken care of. We've got it portability, we've got all that. But then you need all your other things. You need your gas, you need your electrical, you need, some sort of enclosure, powder, dust collection, whatever, right? So there's a lot of other things you need to make that process work, unless you go into an area where nobody cares, right? So if you're in an area where, you can spray in the open air and let the dust fly, that's a different story, but those are few and far between, and they're getting fewer as you go. So now you need to be able to control that space. And that's where we're seeing the challenges. But yeah, logistically, I mean, there's the other, I guess, possibility is logistically, you've got to also bring that hardware to the space. So that's a bit of a challenge. I don't know, Tim, you want to?
Yeah, I'll add to that a little bit, Aaron. I do think there's an opportunity, and talk about future. I think with us being in 9 different countries, and more probably within the next, I'd say, few months, we're looking at, how do we actually make sure that we talked about earlier about cold spray being easy, but it's very hard to do well. We're trying to basically find a way to communicate better with our customer to give them what they need and support them, right? So that extended services we talked about. We're also looking at, visual streaming is one thing we're really looking into as well, and going to support in terms of, direct tie-in to the customer to help them through a process that they may need help with. It's something that we know is going to be part of the future. It's definitely part of VRC's future as well.
Gotcha. Well, thank you for those answers. We're just about coming up at time. And there are more questions that have been asked, but I would encourage y'all, if you have those questions, please, if you're coming to CSAT, go talk to Aaron, go talk to Tim, talk to any of us who are going to be there. That's really what CSAT is for, is to, a rising tide lifts all boats, and so that we all kind of collectively can advance the science of cold spray.
And Sean, I'll just add,
yeah.
Please feel free to use the email addresses you see on the screen there.
Yep.
Reach out if you have questions. Always happy to talk to folks about cold spray. So
absolutely. Yep.
Absolutely. So Tim and Aaron, thank you so much for taking the time to talk to us today. We all really appreciate it. And one quick last plug, if y'all haven't applied or registered for CSAT yet, please do so. If you're planning on coming, we would love to see you there. There's a lot of really good conversations, really great presentations, opportunities to build collaborations, and to see old friends. So we'd highly encourage y'all to come. And thank you, everybody, for taking the time today.
Perfect.
all right.
Thank you, guys. Appreciate it.
Have a good one, everybody.
Take care. Bye.